Hello everyone, and good evening. Welcome to the OneClass channel. My name is Fejiro, and I am an Honors Bachelor of Science graduate working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need any extra help or some help with your homework or any tutoring, please check out the links in the description below. And with that, we're going to hop right into our first question for today. Let me just set it up here. And we have give me a quick second. There we go. We now have question 1 for this session being N2O, so dinitrogen oxide, is linear and polar. Okay? So on that basis, is it going to be NNO or NON? Explain the answer. Let's tackle this one first, actually, just because we can actually figure that out straight from the question. If the molecular and electron geometry is going to be linear, that means that there's no valence electrons here, right? Meaning that the only things that are going to be, in a sense, pulling this molecule would be like the left and right. And the only way for it to be polar overall is if one side had more pull than the other. If it was NON, like this theoretical shape, these two would cancel each other out. This shape could not work because it's polar. Because if, in theory, the oxygen had no valence electrons, then this is the only thing that would be pulling on it. If it had no lone pairs with it, this is it. So with that being said, this wouldn't work because this would be a non-polar theoretical molecule. But NNO, the difference here is that now that nitrogen is in the middle, we have one nitrogen in the end and one oxygen. This, because oxygen has a greater electronegativity than nitrogen, this would actually be the part that pulls in more than the nitrogen on the left side. With this being said, on this basis that it's linear and polar, this, okay, it would be the NNO would be our theoretical arrangement for this molecule. Okay? And now for B, on the basis of the answer in part A, we're now going to draw a Lewis structure of N2O, including resonance forms, and give the formal charge and hybridization. Okay, so the central atom in theory, no matter what the charge is, should be sp hybridized because of the fact that we should have just two bonds there. But instead of jumping that far ahead, we're just going to first draw a Lewis structure. So we know nitrogen based on the periodic table, okay? If it loads, it can give away 5 electrons or accept 3. Point being that nitrogen is working with 5 valence electrons, and oxygen is working with 6 valence electrons. So if we multiply 5 by 2, because we have N2O, we have 10 plus 6, that is 16 electrons to work with. And now we have our theoretical structure here, NNO. So let's start with just one single bond in between, just to be able to start there, okay? And then we're now going to fill in the rest. So oxygen is now sharing one of its 6. So 2, 3, 4, 5, 6, okay? And just to make sure here, based on the question, we have for the nitrogen on the left we have one of its 5, so 2, 3, 4, 5. Okay, and the nitrogen in the middle is sharing 2 of the 5, so 3, 4, 5. Okay, so this is what we have so far. So let's do some rearranging here just to make sure that this works. So what we could do is that we could make these two form a double bond. Let me just draw it in red actually. Okay, so now the shape we have is N double bond here and oxygen. Okay, this is what we have so far, but we want to make sure two things: that there's still the octet rule, and also that each electron, I guess, is, we actually have the correct amount of electrons here. So there's a few things we could do here. We could do a resonance structure to where we could move this electron here over to this side. So now we have, this is one of our resonance structures right here. Double bond still. No, wait, that wouldn't work. Actually, yes. And then we move this to here to form a double bond here. Reason why we just did that is because oxygen still needs the octet rule. So this would be one of them, okay? Another one, this time we're just going to keep focusing on moving around valence electrons, because we can actually move one of these into a bond, okay, forcing these ones out to the nitrogen. So that's what we're going to do here. A possible resonance structure resulting in that would be a nitrogen that looks like this, okay, with just a single bond now. And now there's a triple bond between that and oxygen, okay? And now for the last one we could do is that instead of forcing it this way, we could do the opposite, to where we would force a bond here into that, and then this one will be forced out to the oxygen. So then we end up having this triple bond here, and one bond, and oxygen looks like that. So as you can see, we have quite a few choices here in terms of what we can do, but this will be the three main ones that we can work with, because as you notice, that's the most we can do, because 2 and exactly 1 and 3 on each side, we still want a bond there, so we can't push anything more left and right. So now let's actually find out our formal charges. The way to find formal charges is by using the valence electrons of that element, and then you're going to subtract the elements that, the electrons that are lone pairs, like the lone electrons on it, and they're also going to subtract the ones that are sharing, but the ones that you're sharing you divide by 2. So for example, we start with this nitrogen here. It has 5 valence electrons, so you subtract, right now that's 4 because it's 2 lone pairs, and it's sharing with nitrogen 4. So with that being said, 5 minus 4 plus 2, that's 6, so that's -1. The nitrogen in the middle has 5, it has 0, and it's sharing 4. Whoops, it's sharing 8, 2 on each side, 8 over 2, and that would equal 5 minus 4, that's +1. So we have a -1, +1, and then the oxygen should be hopefully a 0. Let's find out. We have for oxygen 6 now, because that's valence electrons, and it's sharing, well, it keeps 4 by itself, and it's sharing 4 over 2. That is definitely equal to 0. So this works perfectly. And you can see here, everything is still following the octet rule. Now for these ones here, okay, we have, for the one at the top, we'll start there. This nitrogen here, okay, still 5 minus, but it has 6 by itself, and it's sharing 2. So 6 plus 1, that's 7, so that equals -2. So this nitrogen here is 2 minus. The nitrogen in the middle is going to be 5 minus, and then it still has 0 by itself, but it's sharing 8. So then that would be still +1. And the oxygen hopefully should be also +1 because we want a net formal charge of 0, since the actual molecule is a neutral molecule. So we have oxygen, it has 2 by itself, but it's sharing 6. So that's 2 plus 5, that's equals +1. So this is perfect. This is what we would expect because it still adds up to 0. And now for the last one, we have formal charges. We have 5 minus, starting from the left, nitrogen only has 2 by itself, plus it's sharing 3. So that would be, I mean, sharing 6, so that's 6 over 2. So 5, so that's equal to 0 right there. So this would be 0. We don't put anything there. So now for the next one, the nitrogen in the middle, still the same thing. Of the other nitrogens, 0 plus 8 over 2. So that's 5 minus 4, that's +1. And then we have 6 minus, this one has 6 by itself, plus 2 over 2. And that would equal -1. So that's what we have here. So these are the 3 possible resonance structures for this molecule, dinitrogen oxide. So with that being said, now that we've done that, draw the little structure and give formal charges, the hybridization, like I was saying, because the way hybridization works is based on how many things it's bonded to, starting with S. So S hybridization would, for example, be like H to H, because only one bond. And SP would be like BeCl2, because there's 2 things attached to it. It doesn't matter whether it's single or double. It just depends on how many bonds paired you have. The nitrogen here has 2 bonds, so this is going to be SP hybridized. Same thing here, 2 bonds, 1 single and 1 triple. So there's 2 double in the first one, 1 single and 1 triple, so that's still SP for the nitrogen. And then we have 1 triple, 1 single, so this is also SP hybridized. So like I was saying earlier, because you were only dealing with 2 other things attached to it, it was always going to be SP hybridized for any of them. But yes, so now with that being said, how would the multiple bonding in this be described? So the last one we have here, okay, this is the one we're referring to for the last question. Okay, so let's see, how would the bonding be described in orbitals? Okay, so with this, since we have the SP hybridized, the way we describe this is that we would say that it's going to be the, just to make sure that I understand it here, yes, okay, yeah, so because nitrogen has the way you write it in the orbital notation, because nitrogen is right here, it would be helium, starting with the noble gas, 2s2 2p3, and then the nitrogen in the center, same thing, 2s2 2p3. Because it's sp hybridized in the middle, we would assume that's going to be its p orbital. And as you see here, the 2p3, that was signifying, because you know how nitrogen was like this, these 3 electrons would be the p3, and that's actually what was used in creating the triple bond. So in terms of this, it would be the p orbitals from left nitrogen bonding to the p orbital of central nitrogen. Okay, so that is kind of what we're looking at here in terms of this, in terms of orbitals. Okay, and just to be specific, exactly, we're looking at the p orbital, specifically maybe the 2p, because that would be because nitrogen is in the second row. So with that being said, though, let's see how we did. For the first question, since a molecule is polar, correct arrangement has to be NNO, because the fact that if you put it in NON, it'll be symmetrical and they'll cancel each other out. So that's why it has to be NNO, because that's the only way for both ends to be different, and so it results in a polar molecule. For part B, they're showing you how to go about getting your Lewis structure. So that we got the first one here where we have the double bond in the middle. Perfect. And then we got the second one here where we have the triple bond on the nitrogens. And then we have the third one where we have the triple bonds on the oxygen instead. So perfect. And then part C, the outermost p orbital of nitrogen has 5 electrons and need only 3 of those to complete its octet, which is why we have a 2p3. So therefore, the outermost p orbital, 2p, takes part in hybridization, forming the triple bond with the p orbital of the other nitrogen atom. The overlapping orbital is at 1800 degrees. I think they meant 180, but I may be wrong. I'm not sure about that overlapping part, but everything else is good to go for this question. Hopefully you're able to see how we were able to get whether it was polar or non-polar, and based on that what our molecule would be. You saw how we did the Lewis structures and the formal charges, and then we were able to show you what they meant by the p orbitals. So with that being said, we're good to go for this question. Let's move on now to question number 2. Okay, so we have what is the Arrhenius base definition? So, as it says here, actually, okay, Arrhenius bases are usually described by substances that add more OH to water. Okay, so with that being said, when you think of Arrhenius bases, we're thinking of things like NaOH, CaOH2, LiOH. Really just anything that's bonded, like trying to think of another example here of this, like KOH. All of these are examples of Arrhenius bases because their goal is, as you can see, when it dissociates, it's going to dissociate into sodium and water. For each one, potassium and water, sodium and hydroxide. So yes, potassium and hydroxide, calcium and hydroxide, lithium and hydroxide. That's how they would dissociate there. So these are all perfect examples of Arrhenius bases. So that's what we're dealing with here. We wouldn't really count, although NH3 ammonia is known as a base, because we're dealing with this definition here, it doesn't really count as an Arrhenius base because of the fact that it's technically through an equation that you can see how NH3 adds more OH into the water. It would go NH3 plus H2O, okay, turns into NH4 plus OH minus. So there is technically a way, and maybe you can contest it, but the goal here is just to see like when it dissociates. That's why it mentions like aqueous solutions. When these solid salts dissociate in water, that's how it forms the sodium and the hydroxide, the metal and the hydroxide, the metal ion and the hydroxide. So that would be the more clear definition of an Arrhenius base. They start talking about other properties of bases, so like they're bitter, slippery, and litmus paper specifically is blue in basic solutions, so it will be blue in these salt solutions. It's just important because there are like Bronsted-Lowry bases and Arrhenius bases. When you're looking at definition, go by that definition and not whether or not, if you know whether it's a base or not, go what the definition specifies for these type of questions. So with that being said, question number 3. What is a Lewis structure of Sf2Cl2, which is implicated in ozone depletion. That's very sad. Determine its geometry and determine whether the molecule is polar. Okay, so let's start with the Lewis structure here. Okay, so with this being said, CfCl2 carbon, okay, is on the 14th column, so it gives away 4 electrons. Well, not gives away, adds 4 to this. Fluorine, and there's 2 of them, are on the 17th column along with chlorine. So both in their valence electrons are going to be 7. So 7 valence electrons, and because there's 2 of each type, it's going to be multiplied by 4 total. So that's plus 28 electrons. So in total, we need 32 electrons. So with that being said, as I mentioned, carbon's in the middle, and we have 1 bond each, and we're just going to put them all around. So we have Cl, Cl, F, F, and there we go. And you should notice right away that we're going to end up with 32 because there's 8 electrons in every halogen listed here. So 8 times 4 is 32, and the carbon in the middle is already filling this octet rule as well. So this right here would actually be the Lewis structure for Cf2Cl2. And now the geometry, this is where it gets interesting. The electron pair geometry is just based on the things attached to it. So it has 1 single bond, another, so 3 single bond, well, sorry, 4 single bonds, but just think of it as 4 bonds in general. So 4 things. So we have 4 for its electron pair number, meaning this shape is actually going to be tetrahedral. Okay, and now we can go further. How many of these bonds or just things attached to the carbon are lone pairs? 0. So we have a 4 bonds, 0 lone pairs, meaning that the molecular geometry is going to be tetrahedral as well. Okay, so now we know its geometry. Now the question is if it's polar. So think of this molecule looking kind of like this when it's all said and done. Okay, we have that's kind of what it would look like. Okay, we have the chlorine and the F's, and if we drew kind of like a triangle shape, it would look sort of like this. Okay, and there we go. It would look kind of like that. So it looks kind of like a pyramid, like a perfect triangular pyramid, like that there. And then the carbon is chilling somewhere in the middle. The point being, though, is that with this type of shape, it's very important if there's any differences between them. And if the difference is big enough, then this ends up being polar, because now that you see it like this, you can definitely tell that if these two were to pull this way, theoretically, then the molecule doesn't cancel itself because it has 2 chlorines. It will move in the overall direction of chlorine. That's what would happen there. So with all this being said, there we go. With all this being said, we need to find out the electronegative difference between fluorine and chlorine to see whether it's big enough. Sorry, not between fluorine and chlorine. Fluorine and chlorine, to see if it's big enough. Because the thing is that carbon in the middle, although we can find the electronegativity difference between fluorine and carbon and chlorine and carbon, it doesn't tell us the relationship between chlorine and fluorine, because they may either balance each other out or one side may overall just have a stronger pull. So with that being said, chlorine has an electronegativity of 3.16 and fluorine has an electronegativity of if it shows me 3.98. Okay, so there's a 0.82 difference, and for there to be a polar difference in terms of the molecular bonds, because all these bonds here are going to be polar bonds, but because there's a 0.82 difference, that is enough for it to say that there's going to be one side that prefers the charge over the other. And fluorine being the bigger one is going to have the greater negative charge, and chlorine is going to have the greater positive one. So overall, because it's going to be moving like in each of the flowing directions, we're going to have an overall net movement that kind of looks like that. So with all that being said, because we have a net movement occurring, it is indeed polar. So yes, it is polar. Okay, and let's see how we did. So with that being said, Lewis structure, we have it. Yep, there we go. And now, in terms of the molecular geometry, is tetrahedral, as we said. And even though it's tetrahedral, because the electronegativity of CF bonds and CCl bonds, there's a difference in them, which we found, which was the 0.82 difference. That's why it's polar, and that's how we get a net movement right here. So with that, this is correct. Now let's move on now to question number 4. Okay, so we have, how do you calculate the density using the mass versus volume graph? So this is a very good question, actually. But the first thing we have to understand is, what is density? Density as a formula is equal to P is equal to M over V. Okay, that is density. All right. And now they're asking in terms of the relationship with the graph, right? And they want us to know, they want to see if we know what the density would be. So if you think about this, we kind of have to use some mathematics here, right? And find, in a sense, the slope point equation of this. Because, well, not, yeah, actually, we use our rise over run. That's what we use. And remember, rise over run? Rise is the y-axis difference, and run is the x-axis difference. So P is equal to that. And remember, when we're doing the rise over run, another thing that this solves for, okay, would be the slope, M. So I'm going to write down slope because we already have a mass up there, but slope is equal to rise over run. So if we were to graph this, we want the mass to be the rise and the volume to be the run. So if we had a drawing like this, okay, and we had the line like that, okay, and so this would be mass, this would be volume. Our slope is our density, okay, this is our density. Once you calculate how much it went up, so the rise over run, so the rise divided by run, you would get the density. So the density is your slope when it's mass versus volume. Now, the reason why they have mass versus volume is just because typically you have, if I remember correctly, the y-axis coming first. But in the off chance where you had this, okay, same graph, but we have now volume here, and we have mass here. And it's going to look like this still, or maybe it's going to look actually like, as volume goes up, the mass has to go up as well, but so it's going to still look like that, right? But the difference is, though, is that this is going to be the inverse. It's going to be density, it's going to be 1 over density. Because now, if we did our rise over run, it'd be volume over mass, which you can only get if you flipped over density and did 1 over density. So just in case you were given any of the graphs, both of them you can still use the slope, okay? to find your density using that graph. So with that being said, density, yep, is mass over volume, and exactly slope, rise over run, mass 2 over mass 1, mass 2 minus mass 1 over volume 2 minus volume 1. And then they actually provide a graph as well if you wanted to see that. So as we click on this link, oh, I see. We might have to go back to the, hopefully you can take it back. But so exactly, you see here, they have mass on the y-axis, volume on the x-axis, and then the slope, the calculated slope, gave them their density, okay? And let's see, hopefully it loads back up. There we go. And then you see here they got 2 points from it, and they're also able to support here that the density was indeed 1.52. So remember, when you have mass on the y-axis and volume on the x, your density is your slope. And if it was the other way around, the y-axis being volume and the x-axis being mass, your slope is now the inverse of density, 1 over density. Now let's move on to question number 5. We have here for question 5, what is a physical reaction? Reaction. Okay. So, the way I like to state it, and it also says here that physical reaction is a reaction where only the physical characteristics of the objects will change. So that's like shape, size, and specifically the physical state of matter. And examples are boiling, freezing, melting, shredding, cutting, and usually physical changes can be undone. For example, if you boiled it, you can freeze it back, and if you've cut it up, you can kind of like try to glue it together. Although some are harder than others. Point being is that typically you can get the component back to its original form. So now with that being said, I like to think of physical reactions are things that change not intra, but intermolecular forces. Okay, why do I say that? Because if we think of a solid, right, like ice, for example, the intermolecular force, because everything has been slowed down, is more compacted. There's a strong intermolecular forces, hence why ice is held together so tightly. And then when you heat it up, you're adding more energy. The molecules are allowed to move a little more freely, and so the intermolecular forces get weakened. Hence why, so solid shape, intermolecular forces are really tough, which is why it stays in this shape even in a cup of water, for example, like even in the glass. Okay, a liquid, you know, as you add heat, for example, all right, is now going to be where it takes the shape of whatever it's in. All right, and the reason why is because exactly you've now weakened the intermolecular forces by adding heat, because the particles are now moving more vigorously, meaning that the intermolecular forces have a hard time trying to hold it all together. Okay, and if you added even more heat at that point, you've added so much energy that the intermolecular forces trying to hold them aren't really in effect anymore, and it turns into water vapor and it evaporates out. So that's why I like to think of it as well, because even us, like a lot of things are held together, like even like the table I'm working on right now, you know, oranges, apples, a lot of these are held together by a mixture of intermolecular forces and intramolecular forces. Okay, but the intermolecular forces are things that you can physically change, as this one, you know, when you cut into an apple, you bite into it, not combust it, that'd be different. More so like if you were to add heat to it, so I guess if you were to cook apple enough, like just add heat, like put it like in a oven or something, it would eventually lose its shape from solid, if it doesn't catch fire. Hopefully it'll eventually lose its shape from solid and turn into more of a liquid thing. In fact, think of also like when you blend an apple, okay, all you're doing is just loosening up, you're destroying the forces that are holding it together, okay, the forces between them, and then that's how you have your puree, because you still have little chunks of apple that are still held together and missed by the blade. But exactly, you were able to break apart, you were able to, in a sense, take apart their intermolecular forces, which are typically easier to break and can be done just by physical labor. So that's how I like to think of that question. But this is still correct. If it makes it easier, definitely just think of it as, changing the states, like solid, liquid, gas, and also like being broken apart, like crushed and such. So now, with that being said, let's move on to question number 6. We have, for question 6, write electron configuration for Mg and Ar using SPDF and orbital box, and describe the relation between E-config, electron configuration, and periodic table. So with that being said, actually, what we're going to do here is that we're going to actually go through. So let's start with magnesium, okay? So before that, I actually like to just draw my SPDF, like just what we have to go through. We have the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And I don't think we're going too far for magnesium and argon because they're pretty high up there. So let's start with magnesium, okay? So we actually answer the second part by doing the first part. The electron configuration, the total number of superscripts should equal the number of the elements. So like magnesium is element number 12. We should have the superscripts all equal in total 12. And I'll show you how. So we start with hydrogen, okay? Hydrogen is 1s1 because the columns 1 and 2 are your s orbitals. Okay, and that means helium, because it's an exception, think of it as being in column 2. Alright, so helium will be 1s2. So magnesium covers both because it's past that. So right now we currently have 1s2. Okay, and also I also put argon under it because argon is farther than magnesium, so whatever magnesium has, argon will have it as well. So now we move on to lithium and beryllium. So now we're in the second row, but because they're in column 1 and 2, we have 2s2. And then we hop over to where the boron is. So columns 13 through 18, excluding helium, are your p orbitals, and you count through and you'll see that the maximum p orbital you can have is 6. P orbitals can fit up to 6 electrons, okay? So we start with boron. So it'll be boron, carbon, nitrogen, so that'll be 3, oxygen, fluorine, neon. So we've crossed that whole part, so it'll be 2p6, 2p6. And now we need to get to magnesium. That would be 3s2 because it's on the third row, it's in the s columns, and magnesium is the second one. And for argon, it's already past 3s2, okay? Because argon is noble gas right here. So to get to argon, so starting from aluminum, we would have 3p6. That covers the 6 there. So this would be the SPDF notation for it. And just to answer the second question, you will see here that when you add 2 plus 2 plus 6, that's 10 plus 2, 12 electrons. Because that's what they signify, the amount of electrons. And the amount of electrons equals the amount of protons. And as we know, the amount of protons tell you what type of element you're dealing with. And this is only the case to when you're dealing with things that aren't ions, okay? So the pure element, the neutral charged elements, because ions will mess this up. So because we got 12 electrons for its neutral charge, we can assume that it has 12 protons, and because of that, we know that it's magnesium, the 12th element. And you see here, 2 plus 2 plus 6, that's 10 again, plus 2, that's 12, plus 6, that's 18 electrons total. And you'll see here that argon is the 18th element of the periodic table. But now we're not done yet. We still need the orbital box notation. And the way we do that is that we want to indicate based on the different orbital boxes. And I'll explain what I mean by that once I have filled them out. And then I'll also just copy and paste this so you can do this for argon as well. So with magnesium, it's going to look more like this. Okay, the reason being because this will be your 1s, this will be your 2s, and this will be your 3s. This will be your 2p, 2p, 2p. The reason why I have only 3 of them, and as you notice only 1 of the 1s, because each orbital can fit exactly 2 electrons. So we have 1s2, so it'll look like 1, 2, 2s2, 1, 2. But 2p6 is 1, 2, 3, 4, 5, 6. That is the order of how it would fill. So 2p5, for example, would look like this, and 2p4 would look like that. So this is what oxygen would look like, for example. But yes, we have 2p6, and then we have 3s1, 2. For argon, same thing here, 1s1, 2s2, 1s2, 2s2, 2p6, and then 3s2, and then 3p, 1, 2, 3, 4, 5, 6. This would be our electron configuration in orbital notation for argon. 2s, 2p, and 3p, and 3s. Okay, so let's see how we did. So we have exactly 1s2, 2s2, 2p6, 3s2, perfect. Orbital box notation, we've shown it here. And then argon, we have now ending with 3p6, and exactly we've added that extra part. So the element is in period 3 and group 18, therefore it has 8 electrons in its third shell. And exactly, the electron configuration is directly referring to the element when it's not an ion. And you have to be looking at the superscripts. So with that being said, we'll move on now to question number 7. We have spell out the full name of the compound. I would love to, oh, there it is. So, full name of this compound. So we have so first thing is that when you see something like this, okay, this is what you call, I believe, we'll have to check it after just because my name is a little bit rusty, but I do know what the name of this is. It's always whether, you know, whether it's an ester, ether, and stuff. This is what I believe is what you call an ester, okay? An ester is formed by a carboxylic acid plus alcohol, I believe, okay? And what leaves, just that group, would be an H2O. Water comes out. This would be called an esterification, okay? So the carboxylic acid part, all right, would be kind of like this part here. Okay, so we have, okay, this is what the carboxylic acid would be. The alcohol, on the other hand, would be like that. And now you can kind of see how the H2O leaves, because when these two bond, There we have 2 H's, 1 O, they leave, and that's how we get this ester, hence the name esterification. Nonetheless, the way you name it is that we use the carboxylic acid end to, that's how we're going to end it, and it ends with 8. So this molecule is going to end with specifically O8. Okay? So what carboxylic acid do we have? Can we name this? Yes, we can. As you can see here, we have 1, 2. Okay? So with this, because we have 2 carbons, 2, that would be F. So this is ethanoic acid. Okay? Which I believe, no, that's not acetic acid. CH2, I think that might be acetic acid actually. No, nonetheless, as would be the proper form, ethanoic acid. So with that being said, to get O8, we just drop the O8 part, okay? So this part gets dropped, and we should have ethane, let's put some space, ethanoate. Okay? So we have that part. And then the alcoholic part, okay, would be in front of it. So the alcohol here, if we count, we have 1, 2, 3 carbon. So this would be propyl, or is it, how do you say alcohols again? Methanol, propanol, there we go. Okay. But the way it actually goes into this compound here is that we have to drop the anol part, and it's going to be YL instead. So it's going to be propyl in front. So we have now propyl ethanoate, and this will be the name of this ester here. Okay, so exactly, they located the carbons, which is good, and then ethane, OH, so ethanoate, perfect, and propane, it'll be propyl, so propyl ethanoate. So we got it correct. And the important thing here is that we have to recognize that this would be a ester, I believe. Let me just check here. Esters are going to be perfect, yes. So this is indeed an ester, and if we typed in propyl ethanoate, we should get what, and it's also called acetate. So that is acetic acid. It makes sense. So propyl ethanoate matches the picture we were given actually. So this is what we have. The important thing here to be able to name these compounds is, preferably for me, separate them into their carboxylic acid and alcohol, and you should be able to name it from there. Okay. And now let's move on to question number 8. So this question here is asking us, okay, define a formal charge and explain how to calculate it. Organic compounds are most composed of carbon and hydrogen, also may have these others in their formula. Formula charge arrangements work very well for organic compounds when drawing their best Lewis structure. How does CHNO and Cl satisfy the octet rule in organic compounds so as to have a formal charge of 0? So this is more of a conceptual question. The goal of formal charge, okay, so let's write it here, define formal charge. That's pretty much what we're working with today. Okay, so the goal of formal charge is to assign a theoretical charge to a molecule based on, so we have the number of electrons, of valence electrons specifically. So the number of electrons based on the periodic table, like nitrogen, for example, that would be 5 valence electrons. And you subtract, okay, this is an important part, lone electrons. So you can do lone pairs times 2, just because it makes it easier time for you. Lone pairs times 2 plus shared electrons divided by 2, or you can also just say number of bonds, because they should be the same. Actually, no, because I would actually prefer shared electrons, because number of bonds, you could have a triple bond, which counts as one bond, but there's 6 shared electrons there. So let's say shared electrons divided by 2. This is how you calculate formal charge. Okay, so this is formal charge. That is a formula used there, and the goal of these is that, in a sense, for the most, I guess, best Lewis structure in the organic compound, you want as many of the formal charges to be close or 0, because the goal is that once it's fulfilled this octet rule, you want the formal charge itself to be something that makes sense. A good example, as I mentioned, nitrogen. Okay, nitrogen, if I drew it like this, where it had 3 bonds on one side and 1 bond on the other, okay, number of valence electron nitrogen has would be 5. Okay, how many lone pairs? None. Okay, and how many shared electrons? Remember, each bond has 2 electrons in it, so that'd be 2, 4, 6, 8. 8 divided by 2. So that one would actually be equal to +1. This nitrogen here has a formal charge of +1. But if I draw this nitrogen like this, okay, so, and the surroundings were still able to satisfy their octet rule, all right, so whatever was here readjusted itself accordingly. This one would be 5 minus, now it has 1 lone pair times 2, so that'd be 2, plus 8 over 2, whoops, not 8 over 2, sorry, I went autopilot, plus 2, 4, 6, 6 over 2, because there's 3 bonds, okay? Well, shared electrons, there's 6 in total, and that would equal 0. So, given the opportunity, if the elements to the left of nitrogen was still able to satisfy its octet rule, this right here would be the preferred choice of nitrogen, because in this one it has a formal charge of 0. This is what they mean in terms of like trying to draw the best Lewis structure. So as you're going through and you're kind of like rearranging your electrons, trying to make sure everything matches the octet rule, you can go further to see which type of structure it would prefer by checking their formal charges, okay? And now with this, how does CH, NO, and Cl satisfy the octet rule in organic compounds? So let's have a formal charge of 0. So this is just kind of like listing bonds, okay? So carbon, okay? You notice that for organic compounds, we have typically CH4. Because in this, actually, if you did the math, we have 4 for carbon's valence electrons, and this doesn't have any lone pairs, but it's sharing 8 electrons in total, so that's 0. And hydrogen only has 1 valence electron, and is sharing like that, so that's why we have 0 as well. So, and you notice that as we go through, you know, if we want to even do like an acid, for example, where we have like this, you notice that even in something like this, for example, all the formal charges here should be 0. Okay, this carbon here, it has 2 double bonds, so it's sharing in total 8 electrons, and it has no lone pairs, so it's 0. This one here, we assume is just attached to a bunch of hydrogens, and as we said, that'll be 0 as well. This oxygen, it has 6 valence electrons, but in this case it has 2 lone pairs, 1 on each side like that, okay? And because that's 4, so 6 minus 4, that's 2 left, but it's sharing 4 electrons divided by 2, so this is also 0. And then same thing with this oxygen here, okay? It has a bond with the H and a bond with the carbon, and it has 4 valence electrons, so that's also 0, and this hydrogen is also 0. So you start seeing when it comes to organic compounds that the reason why you have these certain shapes, like for example this right here is in it's a carboxylic group, COOH, That's why you get things like that, because their formal charge, right, shows that this is the most stable type of setup it can get based on their formal charges wanting to be 0. So with that being said, we just check through this to make sure and see if we missed anything. Formal charge is assigned to a molecule, assuming that electrons are shared equally regardless of relative electronegativity. Okay, so kind of like what we're doing with the whole valence electrons. Formal charges help us keep track of the electrons in the molecule, and there are two ways which the atoms can satisfy the octet rule. One way is by sharing their valence electrons with other atoms. The second is by transferring valence electrons from one atom to the other. The point being, though, is that you want to satisfy the octet rule, and then you check in for formal charges. One that I can think of on the top of my head, that from a previous question actually, but I'll just draw it here, was dinitrogen oxide. Okay, if I drew it like this is one possible resonance structure. All right, and it looks like that. As you notice here, everything here satisfies the octet rule. Okay, but for the formal charges, we have here nitrogen is going to be 5 minus 4 plus 4 over 2. So that's in total 6. That's minus 1. This nitrogen has a charge of minus 1. And you'll see in the middle, because it's 5 minus 0 plus 8 over 2, it's going to be plus 1. And this oxygen here, as we've shown in the other question, is going to be a formal charge of 0. That is one possible resonance structure. Another one would be something like this. So still the same molecule, just a different resonance structure. And in this case, this one is still going to be a plus 1 because nothing has changed. It's still only sharing 8. But the oxygen now is going to be the minus 1 here, because we have 6 minus 6 plus 2 over 2. So that's 7 minus 1. And the nitrogen here is going to be satisfied because it's going to be 5 minus 2 plus 6 over 2, which is 3, and there's 0. So these two are both possible resonance structures, and these two both have certain formal charges. So with this now, this one is a little bit more nitpicky, because here you have to involve the electronegativity, because the more preferred resonance structure would actually be this one. Reason being because oxygen is a more electronegative molecule than nitrogen. But prior to that, though, as you can see, formal charges just help you construct it, because after you've made sure you fill in the proper octet rule, you then check your charge to see something that makes sense. Because a third possible for this question here would actually have been like this. All right, and sorry, not like that, because it still fills the octet rule for each, as you can see. But now we have a formal charge of minus 2 on this nitrogen, and plus 1 here, and plus 1 there. And that's something you don't want, because although this is definitely a possible resonance structure, literally each element there is away from 0, and it wants to find a more convenient way to at least be close to 0 rather than have these changes that add up to 0. It'd rather have 0 in the elements themselves, which is why this one makes more sense. Okay, so formal charges are a bit tricky, so I definitely recommend that you just review it as well, because it's definitely a useful tool, especially when drawing your Lewis dot diagram. In fact, whenever I draw my Lewis dot diagram, I always check with formal charges as well. So now question number 9. What is the mass of sodium hydroxide? Okay, so with this, thankfully they were able to give us the actual name for sodium hydroxide. If that wasn't given, you would see here that sodium is Na based on the periodic table, and hydroxide is something you have to memorize. Hydroxide is an OH minus, and because we have Na plus and OH minus, that's how we have NaOH to end with. Now for the mass, we just have to add the atomic masses of its constituents. So we have sodium, one of them, plus 1 oxygen, plus 1 hydrogen. And sodium should be 22.99, but it's always good to double check. and oxygen is 15.999. Hydrogen is 1.008. Let's see here, 1.008, perfect. Sodium is 22.990, and oxygen is 15.999. So then we multiply by their coefficient. We still have 22.990, 15.999, and 1.008, and then we add. I always like adding the multiplication step first because that just ensures that I'm not missing anything. So 22.99 plus 15.999 plus 1.008. So what we get here for the molar mass is 39.997 grams per mole. And depending on the periodic table you may use, you could also just get 40. It's just important that we're really close to each other. With that being said, this will be the mass of sodium hydroxide, specifically the molar mass. We would actually not be able to find the mass of sodium hydroxide without giving the moles, because what we've done here is the molar mass, because this shows how many grams per mole. So the real question would have been molar mass, or mass of sodium hydroxide when you were given like 0.5 moles, for example. Then you would use this formula here, and you would find out that you had a mass of 19.99. So things like that. Oh, there, it was asking for molar mass, so that was my fault there. But nonetheless, this is correct though. So molar mass, 39.997, and they got 39.99. And the reason why is because their numbers was slightly different. They had 1 for the atomic mass of hydrogen, and they had 1.008. And although they also had 16 for oxygen, and I had 15.999. So now let's move on now to the question number 10, which is how do you calculate the mole fraction of a solute? So for this question, the way you actually calculate the mole fraction of a solute is actually relatively simple, but the important thing is making sure that you've converted the right things. What do I mean by that? I mean that if you were given something in like moles per liter, so for example, if I was given 5 moles of HCl, okay? So with this, I know that I have 5 moles of HCl, but we actually were given the moles per liter. And the liter in this case, because it's a solution, aqueous solution, typically I use water, so we have 1 liter of H2O. And at standard temperature and pressure, 1 liter of H2O is also 1 kilogram of H2O. So now, because we have the mass, we actually convert this into the you can actually convert this into the, I'm really blanking here for some reason, 5 moles of HCl, so 5 moles per liter of solution actually. So this would be, we have a 1 kilogram total actually. So in this case, if we assumed, let's not make any assumptions here, just because unless we knew as well the density of HCl, for example, then this one could be potentially solved, just because of we need to know how much of impact 5 moles of HCl would be in the water, because that's a certain amount of grams. So that's the amount of grams that would occupy the well, actually we can still do that, because then if we still use the according like the 1-to-1 ratio of 1 liter is 1 gram, we actually have then 5 moles of HCl. That would be HCl is 1.008 plus chlorine is 35.45. Okay, so that's 36.458 grams per mole. And we have 5 of them, so that's times 5. So that's extremely concentrated. So you have 182.29 grams. And if we're assuming that water is 1 gram per liter, 1 gram per milliliter, so then that means we would have, of the 1,000 grams technically, or 1 kilogram, this much is going to be the hydrochloric acid. So if we subtracted that, we have 817.71 grams technically, because we're assuming standard temperature and pressure, of water. Okay, and water, it's oxygen and 2 hydrogens, so that's 1.008 times 2 plus 15.999, and we get a molar mass of 18.015 grams per mole. So then, because we have the grams here, we have to divide by the molar mass, okay, to get how many moles of water that is. And we have about 45.39 moles of H2O as the solvent, okay? This is all theoretical, but the important part here is, now that we have the moles of water and the moles of HCl, we can find the mole fraction. How much of this 5 molarity of HCl is composed of HCl? We divide the 5 divided by the total moles, so it would be 5 plus that 45.39, okay? So that would be 5 divided by 5 plus that. Our mole fraction of HCl in this is going to be times 100, because we need a percentage. I like to do the percentage, but you can also just do fractions. It will be 0.099 fraction, or 9.92% of 5 molarity of HCl is just HCl. So you see how we got the moles of water from the moles of HCl, and we were able to find the mole fraction. The key thing is just knowing how to find your mole fraction. But other than that, once you have found that information, you just divide the moles of the solute, or whatever it could even be the moles of solvent, over the moles of the total moles you have, okay? As you can see here, moles of solute over moles of solute plus moles of solvent. So this is correct, because that's what we did right here. So these are one of the trickier questions they could ask, because this question has, frankly, too many assumptions in there. We assume that 1 liter of water is 1 kilogram of water in standard temperature and pressure. And then we also assume that we're just taking like the grams to gram composition, which is what we were able to do here. And using that, we found the moles of water, and because of that, we were able to now add them together here in order to get the total, which we divided now the moles of HCl. So now with that being said, we move on to question number 11. Okay. How do you convert ATM to TOR? So we're starting with ATM and we're ending with TOR. So it's going to be X amount of ATM, and because we want to end with TOR, we're going to have TOR in the numerator and ATM in the denominator. And now to find out how to convert them, we actually just, it actually says the answer here, 1 ATM is equal to 760 TOR. What we're doing is just double checking this as well. I always like to have a list of conversion factors that are commonly used in chemistry and physics. So with this being said, it is opening. There we go. Units of pressure. 1 ATM is equal to 760 torr. So that's 1 ATM down here, and it's going to be 760 760 torr. So X ATM is going to be 760 X torr. And that is our answer there. So that means whatever ATM you get, let's say it was 3.9 ATM, it'll be times 760, and we'll get 2964 for the torr. As I even showed here, we have 2.5, multiply that by 760, and indeed we do get 1900 torr. So this, for question 11, this is now how you convert ATM to torr. Okay, now just a quick water break before moving on. What is the molecular geometry of CHClO? Okay, great question. For this, we have to actually first find out the Lewis dot diagram. So for this, we actually need to go to the periodic table and see how many electrons each one offers. So carbon has 4 valence electrons, hydrogen has 1, chlorine has 7 valence electrons, and oxygen has 6. This is based on the fact that carbon is on the 14th column, hydrogen is on the 1st column, chlorine is on the 17th column, and oxygen is on the 16th. Now the element that will be in the middle will be carbon, because it has the most amount of lone electrons. Not lone pairs, but lone electrons. You'll see here that carbon looks like this. Hydrogen, like that. Chlorine, because we have all these lone pairs, it only has really one we can use, and that's less than carbon. And oxygen looks like this. So in this case, it only has 2. Which is why carbon is going to be the one in our middle. So we have carbon in the middle, and we have 1 bond to each, and it's going to be Cl, H, and O. So with that being said, chlorine is going to fill out the rest of its 7. So that's 1, 2, 3, 4, 5, 6, and it's sharing one of its. And oxygen is going to fill in the rest, so that's going to be 2, 3, 4, 5, 6 currently. Hydrogen is already done because it's sharing that 1, and carbon is sharing 3 of its 4. So what's going to happen here is that the oxygen and the carbon are going to bond together to form a double bond, and so now we have this shape. CHCl and oxygen, like that. So its shape is going to look something like this. Double bond, C, single bond, and there. So with this all being said, what is the molecular geometry? So first I have to count the amount of pairs it has in the central atom. So the way we do this is just by circling the amount of bonds or lone pairs. It doesn't matter what type they are, we just circle them. So we have 1 here, 1 here. Oh, that's strange. There we go. 1 here, 1 here, and 1 here. So with that being said, that's going to be 3 for its electron pair number. And that is known as trigonal planar. But they're asking for the molecular geometry. And molecular geometry cares about whether you have a bond or you have a lone pair. Luckily for us, for carbon in the central atom, we have no lone pairs. We still have 3 bonds, 0 lone pairs. So the name actually just transfers. And it's still going to be trigonal planar for the molecular geometry of CHClO. Okay, and there we go. It's trigonal planar. The CO and Cl atoms lie in the same plane. Okay, along with the hydrogen as well. And exactly each bond is 120 degrees approximately. And that's what we got. So this is correct. Oh, maybe actually. Because this is a possibility. No, this would be the better shape. I was thinking of something that looks like this. If we did OH on the corner, but the issue here is that now we have carbon with two bonds here and it only has two more. So this would not work. Okay, that's why it has to look like that. And this is correct. Trigonal planar. Question number 13. What is a molar mass of calcium? So, we have to first figure out, ironically, but realistically speaking, we have to know what calcium is. Calcium, if you look on the periodic table, is a metal. Okay, specifically, it's in the alkali metals right here. Okay, and we can actually use the periodic table that's listed down here. You can see calcium right there. Okay, it's a little bit small, but where my mouse is, if you can see my mouse, but it's the 20th, it looks like. Yep, the 20th element on the periodic table. And because it's a metal, typically when you see it in nature, calcium just looks like that. It's a calcium solid by itself. The reason why this is important is because in this case, the molar mass is still the atomic mass of its constituents, but all we have for its constituents is 1 Ca times 40.078, I believe. Let me double check. And because that's all we have, that equals 40.078. And if you add that, we're really just adding itself. So we have 40.078 grams per mole. Because the only constituent here for calcium is just a calcium element. So this is what we have, 40.078 grams per mole. And this is correct. So now let's move on to question number 14. Okay. What are the properties of solids? As you can see here, they actually touch on a very important thing, is that between solid, liquid, and gas, solids have strongest intermolecular forces between solids, liquids, and gases. Okay, the reason being is because so you have all these molecules, close to each other and such, their intermolecular force is so great as to why it can then go on to keep its shape. Okay, like if you put it in a container, for example, it would not, flatten down and take the shape of the container. In fact, even if you had tiny little pieces of solid, like for example, if you have salt, you notice that you can still only fit so much like in your salt container, because the salts, although small, they have a solid shape and they just stack on top of each other to fill in that shape as best as possible, but they will not, be as smooth as a liquid in there, because a liquid exactly will be just one constitution and it would just be filled in completely like that. But in this case, solid has its own shape. That is the key part. It has its own definite shape and volume. Okay, so trickier things like not really metalloids, but if you think of like mercury, for example, it is still like technically a metal or a transition metal, but in room temperature is more of a liquid. And there are things to where if you get into like a certain optimal temperature, you kind of have it to where it wants to keep its shape, but it's kind of melting a little bit, kind of like putty, for example. That one, the reason why I'm talking about that is just because the intermolecular forces there are just a bit weaker to where now there's room for it to expand. because the intermolecular forces aren't able to hold it so tightly. Solids, they're held really tight together, which is why exactly it has its definite shape and volume. And exactly, generally, they do have higher density. And the reason why they have now, specifically that part, the high melting point, is because the intermolecular forces are so strong. Because when you have a very compact solid, like, I don't know if you've tried, and I don't think you should, but in terms of trying to melt salt, not salt water, but just salt, you would notice that that is extremely hard to do, because salt has a very high boiling point. In fact, a very high melting point even, because of the fact that its intermolecular forces are so compact in that solid. Okay? So yes, I like this. This just explains it thoroughly, and this is correct. So yeah, that's what we have for solids. And now question number 15. How many pints in a quart? So for this, because I don't have a unit converter, I'll just refer here to this right here. So according to this here, well, first we have to establish what are we asking for. So we're actually given quarts, and they want to know how many pints are in there. We're going to just, for simplicity's sake, we're just going to say pints to quarts. I know they have here listed US and UK, but let's assume we're dealing with like this in the same country. So with that being said, we start out with quarts. So that's an X amount of quarts. Okay. And we want to be able to find the relationship between quarts and pints. Okay, so according to this, as you can see here, there's going to be 2 pints per quart. So we have 2 and 1, because we have to put the quart in the denominator, and I'll show you why very soon, and the pints in the numerator. 1 quart. And then you will see here that the units actually cancel out to where now we only have the pints left. And based on this formula here, we know that there's going to be 2x pints per quart. What does that mean? It means that whatever value you're given for quarts, so let's say you had 6 quarts, that would be 12 pints. Okay, if you're giving 3.5 quarts, that would be 7 pints, because the relationship here is 2x. Whatever you have for the quart, you multiply it by 2. Okay, and this is correct. And now for question number 16. Which compound contains both ionic and covalent bonds? Okay, so the way to figure this out, we kind of need a few steps here. We first need to figure out what an ionic and a covalent bond is. So to break it down, an ionic bond is typically a bond between a metal and non-metal, okay? And covalent bonds specifically are going to be 2 non-metals attached to each other. Now this question is asking for which compound contains both ionic and covalent, okay? So we'll start with the first one, A, potassium iodide, Ki. So this one has potassium and then iodide. We have the metal and non-metal, okay? So this would be an ionic bond. But do we see any chance of a covalent bond? Unfortunately, because there's no other non-metal there, there is no covalent bond. So with that being said, A cannot be the choice. B, we have CaCl2. Now with this exactly, we still need to kind of know our Lewis dot diagram because we want to be able to see how it's arranged. We have calcium in the middle, and then we have 2 chlorines to the side. Oops, there we go. All right, and because we have this, we can see here that calcium is the metal, chlorine is a non-metal. So from this, we can say that it has an ionic bond that's right there, but with covalent bonds, the chlorines are not attached to each other. Because they aren't bonded to each other, there is no covalent bond here, so B cannot be it. For C, we have CH2Br2. So for this one, it kind of looks like this, where carbon's in the middle, okay, and we have HHBr. So for this one now, we have a bunch of actually nonmetals bound together. We have carbon and hydrogen, which is nonmetal, and carbon bromine, which is also nonmetal. But now the question is, do we see any metals here? Unfortunately, we do not see any metals present in CH2Br2, so there's no ionic bonds here, so this is not it. So that does make our answer D, but let's see why. We have NaCN, which is sodium cyanide. You'll see here that if we drew it out, we would have the sodium, and then we have this. So sodium plus, and then we have CN minus, and the minus will be on the carbon. But this is what we have for sodium cyanide, okay? So we have here an ionic because we have a metal present and a non-metal present, carbon. And we also have a non-metal bonded with a non-metal. So this checks out actually. This right here has the requirements of both a covalent bond and an ionic bond. So indeed, it is sodium cyanide as a compound that contains both ionic and covalent bonds. So let's see here. They actually drew it out for us, kind of like what we did. So you see ionic for potassium iodide, ionic for calcium chloride, and then covalent for 2-bromomethane, I think. And then this one is sodium cyanide, and that one indeed has both covalent and ionic compounds. And that leaves us with D as our answer. Perfect. So now we'll move on to now question number 17. Okay, and what do we have? What are the monomers of carbohydrates? So, for this question, we have to understand, as I said here, monosaccharide, but we have to understand what they mean by carbohydrates. Carbohydrates typically, okay, are referred to as sugars. That is carbohydrates, okay? And another name for sugars are also saccharides. I'm sure you see where I'm going with this. We have now the ending saccharide, okay? If you wanted a monomer of it, which is in a sense non-repeating single unit of a carbohydrate, aka a sugar or a saccharide, you would need to add the prefix mono in front of it, and that would give you the monomer of a carbohydrate, which would be monosaccharides. An example of a monosaccharide, if I remember correctly, would be glucose. Glucose is an example of a monosaccharide. And the cool thing is that when you have a glucose and a fructose bonded together, that's how you get sucrose, I believe. But don't quote me on that. But point being is that actually fructose is another example of a monosaccharide, aka a monomer of a carbohydrate. This is also an example of monomer. So is that glucose checks out, fructose checks out. There are other monomers as well, but just a few that I can think off the top of my head. But yeah, that's what you would think about. So sugars, monomer of carbohydrate, that's monomer of sugars or monomers of saccharides. That's what they call monosaccharides, okay? So that is what we have there for question number 17. So with that being said, this is correct. Let's move on now to question number 18. Is Sf4 polar or nonpolar? So we have Sf4 polar or nonpolar. And so Sf4 is also known as sulfur tetrafluoride. And to find out if it's polar or nonpolar, we do have to go through just a few steps here. So the first thing is find out its Lewis structure, and we know this by figuring out how many electron each element contributes. So sulfur is on the 16th column, which means it has 6 electrons to contribute. You can also double check this based on its electron configuration, because sulfur ends up with neon 3s2 3p4, and if you add it up, specifically the valence part, the third shell, you will see that sulfur is indeed going to have 6 electrons to donate, and fluorine is just helium 2s2 2p5, and you can see here it also verifies that it has 7 electrons to work with, based on the fact that it's also on the 17th column. Okay, so we have 1 6 because sulfur is only one of them, but we have 4 fluorines, so that's 7 times 4, which is 28. And when you add this together, 6 plus 28, we have 34 electrons to work with. All right, so we have sulfur in the middle. Okay, and just as a heads up here, sulfur breaks octet rule. There are a few of them that do this, okay, and sulfur is just one of them. Phosphorus is another one as well that breaks the octet rule. And just the way I remember this is just by think of just adding as many things as you can into the central atom, and then also filling in how many electrons it would have left based on how much is shared so far. So we have S, and we have F's on each side because it's Sf4. Okay, and so we have fluorine, 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 fluorine. Now let's start with the fluorine. Okay, we said that it can donate, it has 7 to contribute, so right now it's sharing 1, so it needs to now add up the rest of the 7. 2 3 4 5 6 7 2 3 4 5 6 7 2 3 4 5 6 7 2 3 4 5 6 7. And sulfur, okay, is so far sharing 4 of its 6. So then, just as I said, sulfur breaking the octet rule, it would have just 1 lone pair right there, kind of squeezed in, okay? And if you're actually to count the amount of electrons we have, each electron circling the fluorines would be 8, so that's 8 times 4, and then plus that 2 more. So it's 32 plus 2, 34 electrons has been satisfied. And to make sure this is the most stable type of structure for sulfur, we would actually check with the formal charges real quick. So sulfur, for example, it has 6 valence electrons, and it currently has 1 lone pair, so that's 2 electrons by itself, and then it's also sharing 8 electrons. So 2 plus 6, okay? 2 plus 4, that's equal to 6, so it's 0. So the formal charge of sulfur is indeed 0, and fluorine, all of them will be the same. 7 will be 6 that it has by itself, that's 3 lone pairs, and it's sharing 2 only. So perfect. This would be the sulfur tetrafluoride. Now, to know if it's polar or not, we need to know the molecular geometry specifically, okay? And this is found through 2 steps. The first step being finding the electron geometry, okay? So with that being said, we have sulfur in the center. If we circle the amount of pairs or things it has with it, it's 1, 2, 3, because each bond, whether it's double, single, triple, counts as 1, 4, and then the lone pair counts as 1 as well. So it has 5. So the name for this, for the electron geometry, would be trigonal bipyramidal. Okay? And now, to actually get the proper molecular geometry shape, we see how many of those 5 are lone pairs. So we have 4 bonds, 1 lone pair, and this shape is called seesaw for its molecular geometry. How does it play into whether it's polar or non-polar? Because now we kind of have it looking like a giant K. Well, in the 2D structure, we have it like this. Sulfur is in the middle, then we have a double bond here, and then we have these looking, let me just draw like double bond here, then we have it like that. Okay, this would be sulfur tetrafluoride, and now you can see here that there's going to be a net movement towards the lone pair, because the lone pair has theoretically the highest electronegativity since they're actually just electrons. So that's why we can actually say based on this that it's going to be polar, okay? Because of specifically the lone pair right here. And just as you'll see how strong it is for the bent shape, you see how we have all these bonds? This, think of it as a shape that looks like that, where there's a circular disc in the middle and a line that goes through like that. But because of the lone pair, well, actually, if you looked at it from a straight angle, it kind of looks like a giant T. That's what we're dealing with. But this bond here actually would be less than 120 degrees because of the fact that typically it would be split perfectly as 120 to add up to 360 in total. That's how much the fluorines are being pushed together because of the lone pair electron. And for these fluorines as well, actually, because this bond is typically that 90-degree angle, this, and so this whole thing here is 180. This whole thing right here from fluorine to fluorine is going to be less than 180 degrees because they're just pushing it. So if we did an exaggerated version, it's going to look kind of like this. That's what it would look like because that's how strong the electrons are. But all that being said, Sf4, sulfur tetrafluoride, is polar because the molecular geometry shows it's a seesaw. We can actually confirm it here. If we scroll down, you would see we have 5 and it's trigonal bipyramidal and seesaw, 1 lone pair, and we have this type of shape. I just drew it sideways instead because that's how I like to visualize it. But yes, so we have the little structure, we see the lone pair, and exactly, I like to go through and draw the shape because of the specific parts that there are some electrons to where they do have lone pairs, but they do end up being non-polar. That's because the lone pairs cancel each other out. So drawing the molecular shape is crucial in understanding what type of electronegative, what type of polar molecule or not you have, whether it's polar or non-polar. So yeah. So with that being said, Sf4 is a polar molecule, and this is correct. So with that being said, let's move on now to question number 19. So for this question, we have calculate the molar mass of sodium sulfate. Neighbor Niceness give us the actual formula. A sample of sulfate with a mass of 300 grams represent what number of moles of sodium sulfate? So calculate molar mass of sodium. In fact, I write out the name. Sodium sulfate. And how many moles in 300.0 grams. So with this being said, we want to first calculate the mass of sodium sulfate. And the reason why I wrote it like this is because if it wasn't, the name wasn't given, right, we would know that it's sodium sulfate, it's Na2SO4, because sodium ions, okay, if you look at the periodic table, that's sodium, and sodium likes to just give away one electron, so that's Na plus. Sulfate, that is an ion you have to memorize, but it is going to be sulfur and a certain amount of oxygens and plus, well, a certain amount of oxygens, and it's going to be 2 minus, okay? The reason why I know sulfate is SO4 2 minus, I actually like to use the oxidation number. It's not always perfectly accurate, but allows us to establish the value. Oxygen typically likes to have an oxidation number of, well, -2, but in this case I just like to say 2, and that means 2 times 4, we have 8 in total. And sulfur, because it's on the 16th column, I like to just say it's 6. Okay, and the trick here is that if the 2 top numbers can be somehow added or subtracted from each other to form the correct amount of, I guess, charge for the ion, then you have successfully obtained the correct amount of oxygens. Okay, and vice versa. If you know how many oxygens you have, if you're wondering about the charge, you can do this as well to figure out, okay, what charge it is. This is just a way for me to double check, because exactly I have SO4 2 minus, and these 2 numbers can be subtracted from each other to form 2 minus. With that being said, though, okay, we have, actually let me just leave it there, it doesn't do any harm. We have 2 minus and we have only 1 plus, so then to balance it we need 2 of the sodiums, and that's how we get in total Na2SO4. So now let's go ahead and add the constituents. So we have 2 Na, so 2 sodium, and we have 1 sulfur, and we have 4 oxygen. Okay, so sodium is 22.990. Sulfur, if we look at the periodic table, is 32.06, and oxygen is 15.999. So we have 22.990 times 2, 45.98. Sulfur is still 32.06, and oxygen is 15.999 times 4, 63.996. And when you add that all together, plus that, plus 32.06, we get the total molar mass, as this question was asking, because we added the constituents, is 142.036 grams per mole. So that is the answer we're going to get there. Now the next part is asking us how many moles are in 300.0 grams. So for this, we actually have to make sure we do this correctly, okay, in terms of converting properly. We have 300.0 grams. And now we have the molar mass. So in order to get the grams to cancel out, we need to make sure the grams now is in the denominator. So we have 142.036 grams per 1 mole of Na2SO4. So then we would now just divide 300 by 142. Reason being is because you can see here the grams do indeed cancel out, and we get in total 2.11. And here we're going to actually notice our significant digits. Because they gave us 300.0, we're going to assume here that they wanted 4 significant digits. So we have 2.112 according to my calculator moles of N, there we go, Na2SO4. So this is what we should get for the moles in 300.0 grams. So let's see how we did. It's like they added the constituents. They got 142.01 only because their oxygen was 15.99 and not 999. Sulfur was 32.07. So just a little bit of variation here and there based on our numbers that we used. So with that being said, then they divided the 300 by that amount, and they got 2.113, which is very close to ours, so it's still correct. It's just important that when you are solving these questions, you always want to refer to the periodic table that you were given, because as you can see, the numbers can vary based on the periodic tables you're using, okay? And exactly, they have the right units and everything for this question, so we are good to go. And now for question 20, we have, let's see here, what is question 20? We are going to find out together. Well then, shouldn't take this long to load. Let me just check out the other tabs. Let me see here of what I can do briefly. I'll be right back. And we're back. Okay, not too long of a wait, just had a bit of a time loading. And this question is asking the electron configuration of CR. And you can probably see the answer there based on what the screen is showing. We're going to work together just looking at the periodic table, how we can get that electron configuration for chromium. Okay, that's what CR is. That is right. If I can find it, there we go, chromium. So we want the electron configuration for chromium. So chromium is element number 24. Okay, so now we're going to go through the same process of what we've done for previous questions, but just to list it out here, we have the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and just end with the 5s. Well, actually, we can just go through and do everything else. 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p, and there we go. Okay, so the reason why I draw like this is because usually we use an arrow to indicate, or just crossing out that we've crossed it. Okay, so element number 24, the way it works, okay, if I were to draw the periodic table, okay, is that, there we go. All right, so with this being said, let's split it here and here, and let's highlight this part. So the way the SPDNF works is that this right here, okay, is going to be your s orbitals. Columns 1 and 2 are your s orbitals. Okay? And if you skip now to columns 13 through 18, not including helium, so if we actually were to do this, helium, no. Helium counts as there. So helium is actually counting as an s orbital. But for the rest of them, this is your p orbital, okay? And they count as in P1, P2, P3, P4, P5, 6. So P, the maximum it can have is 6 electrons. And S, as you can see, because there's only 2 columns I referred to, is just 2 electrons. D orbitals, which is the next one, is going to be your middle from columns 3 through 12, consisting usually of just the transition metals. So this would be your D orbital, okay? And this one can hold up to 10 electrons, which also coincides with the amount of elements there are spanning the D orbital. Well, not the elements in that row. If you count from scandium to zinc, you have counted 10 elements. And the reason why I highlighted this part is because this is your lanthanum and actinium series, and that's your F orbital, and that one can hold up to 14 electrons. And you can see here, if we did from the lanthanum, you should be able to count 14 electrons here, okay? 14 elements. All right, so that is how it breaks down. With that being said, let's go ahead and find out what chromium is, okay? And I'm actually going to draw something else as well to match this, and that's going to be the orbital notation. So we're going to have boxes for each one. So as I mentioned, p orbitals can hold up to 6 electrons, and each orbital, or each suborbital in that orbital, if that makes sense, that subshell, can hold up to only 2 electrons. So this right here would be your p. Okay, so you just you can label how you want. So I'm just going to do this right here, and this would be your S. And we're just matching because this is going to be the 1, 2, and now this is going to be a 3. I'm only going to go down to 4 because that's how far chromium will go, as you will notice. Okay, this is your P as well. This is your S. And then for chromium, we actually have 5. Okay, so this would be your D orbitals. Okay, and then we're going to have one more S down here. Okay, let me just actually do this. Move this a little bit lower. And the D orbitals. Nope, that's not enough. Okay. It's going to be like right here. And I'll show you why soon. It's too low. Okay. Around here. There we go. All right. So we're going to first focus on this side here. So chromium, element number 24. All right. We're now going to just, in a sense, count through. As I said, hydrogen and helium are your 1s. So we cross that. So right now for chromium, we have 1s2, hydrogen, helium. And then the next up, as we count through, is lithium, beryllium. That would be your 2s2. And then we go from boron to neon, which is 2p6. And then we go from sodium to magnesium, which is 3s2. And then from aluminum to aluminum to argon, that's 3p6. And then we now drop down to 4, which is potassium and calcium, and that would be 4s2. And then not 5, but you can see here that chromium is actually in the d orbital here, And the trick for d orbitals is that when you get there, as you can see here, as we've been crossing these out, because we just finished 4s2, you actually start with 3. Okay, so even though we're on the 4th row, that would actually be 3d, and the scandium is 1, titanium is 2, vanadium is 3, chromium is 4. So it'll be 3d4. Okay, so now for this, the reason why I'm zooming out is because if we were not to translate this into these shells, into these orbitals, we have 1s2, so 1, 2, 2s2, 1, 2, 2p6, which is 1, 2, 3, 4, 5, 6, 3s2, which is 1, 2, 3p6, which is 1, 2, 1, 2, 3, 4, 5, 6. Then we have 4s2, which is 1, 2, but we have 3d4, which is 1, 2, 3, 4. Now, I'm actually going to tell you right now, this is the wrong electron configuration for chromium, okay? And not because we didn't organize it right or anything. It's because of actually this subshell right here, okay? Well, I'm just going to highlight, I'm just going to say like that. This subshell right here is going to try to do something wonky. And what do I mean by that? I mean that if you look at it, this d orbital is so close to half being filled, and that's why I drew it here, because in a sense the energy between the 4s, the 4th one here, so there's 1, 2, 3, 4, and that 3d are close enough to where actually the electron here is going to vanish, well not vanish, but going to move up into that d level here. So this would actually be the more stable or more preferred electron configuration for chromium because of the moving of electron from here into this orbital, because now this orbital is now half filled. With that being said though, what would our electron configuration be? Now mind you, I like to organize by number, so there's two ways to write this, which I will, but we have now 1s2, 2s2, 2p6. Let me just zoom in to get back to normal what we were working with. 2p6, 3s2, 3p6, 4s, as you see here now, 1, 3d5. You can also just write it as 3d5, 4s1. Both are the same thing, but the important thing is that you have a 5 now and a 1 here, okay? And to make sure that we got the actual one for chromium, we just add up all the superscripts. So that's 2 plus 2 plus 6. So 2 plus 2 plus 6 plus 2 plus 6 plus 1 plus 5. And we do indeed get 24, and that is the element number for chromium. So the other way you can actually write this as well, if we took all of this part, because this is going to be signifying the most recent noble gas, which is argon, we can just write AR, and then it's just going to be 3d5 4s1 or 4s1 3d5. Either way works, but this would be the actual configuration for chromium, specifically because of this change in the orbital here. This would be the electron configuration for chromium, okay? Let's see how we did. If it loads, oh no, okay, there we go. Using the off-bow principle, which is what we did earlier, we see that we get 3d4. But we checked for the half-filled d orbitals, and we removed an electron from the s orbital in the 4s to make it now half-filled. And that's how we got 4s1 3d5. So with this right here is correct. All right. And exactly, you can write it either way you want, but as long as you know that it's 3d5 4s1, solution is correct. And with that being said, that is actually going to be the last question we solved tonight. I just want to thank you again for joining me. If you have any further questions, definitely check out the links in the description below. Even if you just need some extra tutoring just to cover the materials we covered today. Other than that, though, I just want to thank you again for joining this stream, and you have a great rest of your night.